In this video, we're just going to wrap up the last few examples from our discussion of the basic theory of linear second-order differential equations. In the previous video, we asked the student to try and find a second linearly independent solution to our differential equation, assuming one solution, y1, was known by using Abel's formula for the Wronskian, if necessary, and using the identity that was discussed in the previous video. It's occurred to me that the student will probably find these videos more useful if they are taking notes, at least some notes, while watching the videos to help with the continuity from slide to slide and video to video. There is a lot of information to make connections here with these videos, and so that's just a suggestion for whatever that's worth, that I hope will help you find these videos more useful if you'll take a few notes as you're going along. I probably could have put a lot more information on this slide to help you remember. So if you need to, I would suggest you go back and watch the previous video again if necessary so you remember what that was all about. Here we're just kind of wrapping things up, finishing the solution to the three examples which you hopefully have tried, and just kind of wrapping up loose ends to finish off this section. So in example 7a, we had the Wronskian, which we found previously from Abel's formula, and then from that identity which we discussed in the previous video, we have y2 over y1 prime is the Wronskian over y1 squared. We're assuming y1 equals 1 as our known solution. So that just gives us y2 over y1 prime is a constant times e to the x. That's easy to integrate. So integrating that, we get y2 over y1 as a constant times e to the x, which we then solve for y2. That gives us y2 is c e to the x times y1, but y1 is just 1 here. So y2 is c e to the x. And remember, the whole idea here is just to come up with a second linearly independent solution of the simplest possible form. So we'll leave out the constant and just wrap up this part by saying the second linearly independent solution that we found is y2 of x is e to the x. For part B, we found the Wronskian is a constant from example 6 by using Abel's formula. Then that identity becomes y2 over y1 prime is a Wronskian over y1 squared is a constant over e to the 2kx, because we're assuming y1 is e to the kx is a known solution of our differential equation. So just rearranging that a little bit, we have y2 over y1 prime is c e to the minus 2kx. So we integrate that and redefine our constant and get y2 over y1 is c e to the minus 2kx after integrating the previous expression. Then we solve that for y2 and get y2 is c e to the minus 2kx times y1. And then we recall y1 is e to the kx here. So we plug that in and simplify and just get c e to the minus kx for our second solution. And again, all we're trying to do is come up with a second linearly independent solution of the simplest possible form. So we'll just leave off the constant there and just say our second linearly independent solution is e to the minus kx. The third example that we posed in the previous video, the differential equation was y double prime plus y equals 0. So the middle term was absent. There was no y prime term, so the coefficient of y prime would be, which is p of x, would be 0. So then the Wronskian is constant from Abel's formula. And in this example, we're thinking of y1 as cosine x as being a known solution to that differential equation, that's easy to verify by taking some derivatives that indeed works in that differential equation. So then if we want to use that and use our identity here to find a second linearly independent solution, we plug in the Wronskian, which is constant from Abel's formula. We plug in y1 squared, and we get a constant over cosine squared, which is the same thing as constant times secant squared for the derivative of y2 over y1. So y2 over y1, integrating both sides, is just the constant times the integral of secant squared, which is tangent. We're leaving off another constant of integration here because we're just trying to find a second linearly independent solution, and if we leave off the constant, we'll have our second linearly independent solution in the simplest possible form. So y2 over y1 is a constant times tangent x, which we then solve for y2 and plug in y1 is cosine x, and of course tangent x times cosine x is just sine x. So that gives us y2 is c sine x for our second linearly independent solution. And again, simplifying that just a little bit makes it a little more convenient to work with. Our second linearly independent solution, we'll say, is sine x to that problem. So the general solution of y double prime plus y equals 0 is c1 cosine x plus c2 sine x. That's the takeaway from that example. And a little more general statement would be the fact that the general solution of this differential equation, y double prime plus k squared y equals 0, has this form. That's a differential equation that you're probably going to see again in the chapter, and it comes up a lot in applications, as we'll see. Be careful you don't get that confused with the similar differential equation which we looked at earlier in the chapter, y double prime minus k squared y equals 0. Watch out you don't get that confused with this thing.